Noam. I've been doing research for the past 10 years, starting in physics and transitioning to machine learning 7 years ago, I think. I lead the machine learning team at Deepchecks. So if you liked what you see today, you know who to come to, and if you didn't like it, it's the dev's fault. Deepchecks itself was founded three years ago, and what we do is develop products for continuous validation of machine learning models, which for us means two major parts. It means validating the data in the model before they're put into production, which means during the stage when you have your data, when you're doing your methodology, when you're training your model, and when you're validating your model, signing it off to upload it to production, for which we created the Deepchecks open source package, which you can find under the name Deepchecks right now on GitHub. And the second part is monitoring the model in production. A bit similar to what Clearmel said. We have for the monitoring, we have an open source version and also a paid pro version. So we also have an end-to-end open source solution, even though to a slightly different domain. Just in a couple of brief points, we're going to talk today about why you should test your ML pipelines, how to do that using Deepchecks, and we'll see some things that were supposed to be live code examples, and we ended up with some HTML printouts of notebooks due to technical reasons, but pretty much the same. You can still see the code, you can still see the results. So let's start. First of all, why test machine learning? Why treat it differently than how you treat testing code? So a couple of differences between just software project and machine learning. First of all, in code, changes are pretty clear. We have Git works like great. That's pretty much what you need. We just heard from Clearmel about how data, model, pre-processing code, training code can all change independently until we all live in a ClearML utopia in which everything is linked and it's a single thing. We are exposed to more risk for parts changing in our system without us being able or even aware that they changed. Second point is in code, it's pretty easy to define coverage. You build some tests, you know that you're running all your lines, so you know you're covered to most cases. Of course, you can also still have bugs, but it's measurable, it's traceable. For machine learning, you can never know how your model will work on new data. You know how your model, even on your training data, you usually know only a couple of metrics that you decided to measure. You don't know the whole story of your model's performance. So there are always blind spots, and you should treat it differently than how you just treat coverage in code. And the final point is that silent failures are more common in machine learning. It can happen in code, sure, stuff will work, but not the way you expected it. But in machine learning, it's really common. Let's say, for example, you have your tabular model, or let's say you have a table. You switch two columns. Now the model still works. It still predicts. You still get results, but they're worth nothing because you didn't notice, but you switched some columns. So unless you test for that, for example, you test the distribution of your columns, you'll never know this happened until you really deep dive manually. So top level perspective, things you should be validating is your data, your model, and your method. When I talk about method, it's the code that you're using to produce your model from your data. And all these three should reflect the things that you want your model to do. The model at the end needs to be in production. It needs to serve on some real data. You need to get good results on this new data. So you want to build your data set to match this real world. You want to build your model in a way that will be able to generalize. And you want your model to produce your method to produce such a model. You want it to be. You don't want to have any kind of leakage. You don't want your method to produce to operate on data in a way that will produce a buggy model. So these three components. I just wanted to give a couple of examples to problems that you can have. So first of all, you can have data integrity problems. For example, you use Toloka, you got some labels, But you have a couple, you don't notice, but you have a couple of very similar images that have different labels. Or you have the same, if I go to a methodological flaw, you have the same sample or very similar samples in the training set and in the validation set. Going onwards with problems we can have with the model itself. So maybe you measure the metrics for your model and they turned out fine, you know, your accuracy is fine, precision is fine, recall is fine, but you have some critical subsegment of your data that is not performing well, for example, some important customer base, and you're not aware of that unless you decide to do that explicitly or manually. Your data distribution can change. The data that you've trained on could be not representative of the data that you're getting in production. Also, data in production changes. So something that worked a week ago may not work now. And last, you can have other kinds of methodological flaws. I gave here one example for such a flaw. One example in the domain of vision is shortcut learning. This is, I think, quite a famous example. I guess some of you know it from the paper, Why Should I Trust You? This example is had a data set of huskies and wolves, and they trained a model to predict the class. Is the wolf, is it a husky? And the model used the fact that huskies are more photographed on a green background in your yard, in your neighborhood, and wolves are photographed in nature. You know, the background is snow. So the model trained on this data will naturally learn that green means husky, white means wolf, and will ignore the most important feature that huskies are cute and wolves are less so. So this will give you good results in your training data set, but in validation or in production, you'll get really horrible results. And that's something you can avoid preemptively. So our philosophy about when you should validate your machine learning pipeline is as early as possible. So can I have a couple of thanks. First thing, you get your data. That's okay. You have your data. You validate your data. First thing, you can check for duplicate samples. You can check for labeling issues. You can check for outliers. Next, you want to split your data. You want to create some kind of validation set. So at this stage, that's another. At this stage, you want to see how does the distribution of my validation set behave compared to my training set? Do I have any issues of leakage? That's something you can check before even the model exists. Once you had that and you trained your model, now you can go and deeply validate your model. What that will include, apart from metrics, that will include analyzing different segments in your data. That will include analyzing your model's robustness, and also comparing it to various benchmarks. That's just to name a couple of examples. And last, once you sign off your model, you put it in production, you want to monitor it in production, track its performance, track data drift, track how well you're expecting it to do in the real world. And of course, you iterate, you retrain your model, and you go over stages on the left side of the slide again. And I'll give later on examples for each one of these three points on the left. I just introduced you to a whole lot of problems, so it's on me to give a solution. And the solution we built is the Deepchecks testing package. And our philosophy when building this open source package is that, of course, it should be, as every open source tool should be, it should be extendable, it should be customizable, you should be able to do with it whatever you want. But our philosophy here, it should work out of the box. It should give you some significant value just using a few lines of code. So all the tests, we call them checks in the package that we build, have some kind of pre-configured setting which just runs on your data, and you'll get some notifications of stuff that is not going well right from the start, and then you can start configuring stuff. I do acknowledge that there is another class of testing in machine learning data and models, which is setting concrete thresholds. For example, I know the age column, age goes from 0 to, let's say, 120, and until now, maybe that will change. But I know that, so I can define that. That's a different class of testing, currently not in Deepchecks, but down the road, check on us and it will be there. Just a word about package. The package currently has support for tabular data and a better support for image data. I think that's the first time we're we're presenting it for computer vision in public. I think it will. We're expecting to announce the end of the beta in the following weeks. So you're getting a very first sneak peek for this package. Of course, you can already install it. It's open source. Just a couple of words about how Deepchecks is built. Deepchecks is built from 3 components. Main one is checks. Checks are what we call tests. They run some logic on your data or on your model. They produce some result, the result of the computation, and they produce a display that you can watch to try to understand what went wrong, what did the check find, what should you do about it. Second component is a condition. After the check has run, there's some kind of condition decides did the check pass or not pass for me. When something that didn't pass means I probably need to fix something about my machine learning pipeline. For example, very simple example, I have a check that computes the metric, for example, precision. Then I will add a condition that will set some threshold on that metric. That's like the most simple example that I can think of. Third component is suites. Usually when you run tests, you don't run only one test, you run a collection of tests that are suited to your problem. So a suite is a collection of checks with their conditions that run together, same API as a single check. You can also combine them nestedly however you want. When you run a suite and you look at its display, it will have some summary display for all the checks inside, what failed, what passed, and what can you see about the checks that failed. So on the left, that's an example of a check display. That's from a notebook. So the check you have some words about what the check does, and then some images explaining what happened in the check, what did it find. In the middle, we can see a result of a suite that summarizes what checks passed, what checks didn't pass, and you can click on them and go to the displays of the individual checks. And on the right, we have an example of how to define a new testing suite. You just create a suite, give it a name. I think, the resolution is not so great, but basically you add the individual check objects and you can add conditions on them, like you see here, .add condition such and such with default thresholds in this case. So pretty simple API. Just a word about how a design choice we made in the vision package. A lot of checks are related to the analyzing distribution of your data. For example, outliers, we want to find outliers in your data, or we want to find data drift. We want to find places in which the distribution of your data is different between train and validation or train and production. So in order to do that, in computer vision, we define a set of pretty simple properties, everyday computer vision properties, brightness, contrast, colors, etc. You can also define your own easily. And we use them for various tasks. For example, finding outliers. Here on the top, you can see very bright images or very high and low contrast in the middle images in the outlier check, which is on the left. On the right, you can see an example of analyzing distribution of brightness between the train and the test data set. You can see the test data set is significantly darker than the training set, and perhaps that should make us worry and perhaps check what's going on. Yeah, so that's about the package in general. I think I owe you a couple of concrete examples. So let's go to the code examples themselves. By the way, all the code examples are from our documentation. So apart from you, of course, getting this presentation, you can also see everything in our documentation. Cool. Yeah, it will be shared in the email. So first example is a data check. That's something that you can run right at the moment that you got that you collected your data set, you registered it with ClearML, but you didn't do a split yet. You don't even think about a model yet. First of all, you validate your data. And here the example we can see is checking for outliers in the distribution of the labels. This is an example of an object detection task. So the labels are bounding boxes. And essentially what you do, you can see I abstracted away the loading of the data set right here. But you basically define the check and you run it with the data set and you get the result. And if you're in a notebook, the result will just print a display. If you're not in a notebook, you can export to HTML or pop-up window or whatever works for you. So what this check found is, sorry for the funny scrolling. So looking at the size of the bounding box, we found a couple of outliers, a couple of bounding boxes that encompass the whole image. So technically that's okay, that's legit annotation, but we may think that our model will have a harder time working with detecting objects that encompass the whole image, depending on the structure of the rest of the data set. Second example, we found some outliers in the distribution of the number of bounding boxes in the image. So looking at these examples, which are all outliers, we can see that there are a couple of annotations that we simply wrong. Like we didn't find all the broccoli here, and this box that certainly doesn't refer to anything. So some of these are samples that I should be modifying. I should be fixing before I'm letting any kind of training procedure to run on this data set. That's something I can know even before I started thinking about a model. Second example here is a check that runs at a stage where you have a training and a validation set, when you have your split, but you don't have your model yet. There are some things that you can check for. For example, leakage or shortcut learning, like we showed earlier. So what does this check do? This check checks if there's a correlation between the properties of your image and the label. Because we use pretty simple properties here, brightness, contrast, colors, etc. We don't expect them to be able to predict the label. If you can predict the label of your data simply using, for example, brightness, maybe you don't need a machine learning model. Maybe you can use something simpler like a if condition. So we expect if you find something like this, it's probably a problem. And on top of that, if something doesn't, okay. On top of that, if we find that there's a significant change in this correlation between train and test, for example, there's some big correlation in train and this correlation does not exist in test, then we know we're onto some leakage that we should, even before we train the model, and we should modify our split. So here's an example, a simple example. We took MNIST, introduced some higher brightness, mean brightness to samples from classes 7, 5, and 0, I think, yeah. And we in the training set, and we can see that these properties, for brightness, now brightness is highly correlated with the label for these classes in the training set, but not in the test set. So pretty simple example. What happened if I test our Husky versus Wolf data set from before? So in this case, I loaded it, and forgive me, I ran it as both train and test, so we don't get the difference, but we do get the fact that both the property mean green relative intensity and the property brightness are both pretty predictive of the class, which is exactly what we'd expect from seeing the data set earlier. Brightness, meaning white, is really indicative of being a wolf, and green is really indicative of being a husky. So we got this check could have saved some time running Lime and some kind of and complicated explainability algorithms in the paper we saw earlier. You can see it right here. Last two checks are in our model evaluation suite, and you apply them once the model is already trained, and you want to know if it's fit for production. For this check, which I like very much, it turns the concept of augmentation, and it asks, what if we apply some test time augmentations? Let's see how well your model does when we apply some augmentations to your data. And in this example, we again took MNIST for simplicity, and we applied, in this case, the shift scale rotate augmentations from augmentations. That's what runs by default. Of course, you can pass any augmentation that you want, augmentations, torch, whatever. And we can see that this augmentation basically is not supposed to change the class. Like 4 is still 4, 9 is still 9. 2 kind of changed. I'll give it that. But we can see that there's a significant drop in performance, in both recall and precision, for this augmentation, which means we have some homework to do. We need to go back. We need to add this augmentation to our training pipeline. we probably should be able to predict on these classes. We shouldn't see this drop in performance. So that's something this check can uncover for us before we deploy any model. Last one, which is applicable both for validation but also for monitoring, is checking for drift in the predictions of the model. So apart from checking the drift in the distribution of properties of the data itself, it's very useful to check if there's any drift in the predictions of the model. We're looking here at a scenario in which you have your data, and you have some batch of new data, and you're making some predictions, but you don't get your labels yet. It's very common that labels will arrive later, next hour, next week, next month, next year. Sometimes labels are not immediate, but the prediction is immediate, and we can use the distribution of the prediction to understand that something has changed in the data. So to look at a very simple example, just start by comparing MNIST train test splits, which are obviously the same. Classes are predicted in pretty much the same frequency between train and test. Then we go on and introduce some, also the metrics are pretty much the same, recall and precision. We introduce some drift. We add some images with a different label, with a wrong label to the test data set, imitating a situation of concept drift in which I have new samples whose relation to the label is different than what I know from my training data. And of course, when I apply the check to that, I see that the predictions the model is giving vary. I have now a different frequency for predicting each of the classes. And if I'll add a condition to that, you can see here the add condition drift score less than, which without any parameter here will result to the default value, which is in this case, I think 1.5. You'll see that adding this condition and running the check, you'll get the same display, but with a bar that says that this check has failed. And also, if you'll check it programmatically, check like the result dot passed, you'll see a failure here, meaning something bad has happened. And later on, we get our labels, we test that, and we see that indeed performance has declined significantly. And checking this when doing the prediction, and even if we don't have a label, can save us some precious time fixing problems earlier on before we actually get our labels. Just to to finish with a good taste, pun kind of intended, we'll go back to the food data set that we saw in the last two presentations. Here are a couple of setup, just code I copied here from the ClearML presentation for the ClearML code. The only thing you need to do before you can run Deepchecks checks when you have your own data set is defining this interface class, which tells Deepchecks how to translate from your image to an accepted format, how to translate from your labels to an accepted format, how to do inference with your model. It could be a couple of lines like here. Once you define that, you define a dataset object. Here I do a couple of validations to see that I define this dataset object well and that I get actual images. And then what I'm doing here, sorry for the scrolling again, is just import one of Deepchecks built-in suites, which already contains a lot of checks that are applied to model evaluation and the default conditions. And I simply run it on the dataset as is. And these are the results that I get. So when it's collapsed, that's a suite result. When it's collapsed, I have these sections, didn't pass, other, which are checks with no condition on them and didn't run, which usually are checks that apply to different tasks than what I'm currently running on. For example, object detection versus classification. So let's see a couple of checks that failed here. We have class performance that failed. We have simple model comparison, and we have segment performance. Let's take a quick dive. Class performance, very simple check, compares the performance of train and test. In this case, we can see that performance on the other class has declined significantly in test. Maybe Moses, next time we should have trained more than 4 epochs. But yeah, it's not a fair comparison, but that's something you want to know about it. You want to know about. Second example here is a check that compares your performance to a simple model. In this case, the simplest model that you can think of the one that always predicts the majority class. So what this check tells you is we build this model which always predicts the majority class. And yeah, it did a bit worse than you in F1 on the relevant class, on the solid class, but not so much worse than you. Like maybe you should improve a little more. Of course, this threshold is configurable. You can tell the check, okay, let me know only when I'm as good as the benchmark model or less good. In this case, the default condition is, even if you're really close, maybe you want to know about it because this model is pretty much a low bar. Last one, segment performance. In this case, we compute the performance for different segments of these properties. It could be our properties, it could be properties that you're passing. And for example, we see here that for certain band of green, samples that are less green, but not the least green in the whole data set, we get really lower precision compared to the rest of the data set, 0.6 compared to 0.8. We can use the package to compute this property, the greenness, on your own data set, retrieve these images and see like what's wrong with them. Is there something specific that characterizes these samples that perhaps I should be fixing? Yeah, so basically that's it. I try to walk you through why we should be testing our data and model and why we should be doing this programmatically and thoroughly. And we try to propose this solution, the Deepchecks package that includes a big set of thought of pre-configured checks that is, of course, configurable, editable, and everything that you expect from an open source package. And like the take-home message is validate as early as possible, data, split, model, whenever you can, you should add these validations. Yeah, I think that's it. If you like the idea, would really appreciate if you check it out, try our package, give us feedback, join the Slack group, and of course, star us. It's an open source project, so that really helps us to reach our crowd and reach people like you. That's it. Hopefully it was interesting.